Welcome back. Now it's time for one of my favorite sections of this Imagine Aviation conference, the chance to hear from and talk to some of the brilliant student partners in our University Leadership Initiative. Our first presentation is a discussion regarding hyperspectral communications and networking for ATM, featuring the work at the University of South Carolina. So it's my pleasure now to introduce Professor of Electrical Engineering from the College of Engineering and Computing at the University of South Carolina, Dr. David Matolak. Dr. Matolak, welcome to Imagine Aviation. I'll turn it over to you to briefly introduce your team and begin your presentation.
Thank you, Steve. Great to be here. This is an exciting event. I will give an overview of our work, and then the students, Priyanka Sinha of North Carolina State University, Mahfouza Khatun of Boise State University, and Zinat Afroz of University of South Carolina, will follow with some details. So let me now share my presentation so that we can begin. Okay, hyperspectral communications and networking for ATM. This is an investigation of air-to-ground and airport communications to increase future aviation safety and efficiency. Why are we doing this? Well, civil aviation is growing and expanding, and in order to meet the demand and make aviation safe, we need reliable communications, and that's what we're investigating. Another reason why we're doing this is because wireless communications is a fascinating area to study. It's broad, and to do this properly, we need to understand wireless channel propagation, communication systems engineering, networking, and signal processing, and other areas. How are we doing this? We're designing and testing dual-band radios for air-to-ground use that are more spectrally efficient and more robust than existing systems. We're also quantifying airport millimeter wave communication channels for use in future airport networks that will be used by both consumers and airport operations. We're also devising drone detection and localization technologies that will enable us to detect unauthorized drones. In the diagram shown in the figure, you can see that most civil aviation is divided into different what we call phases of flight, such as taxi, takeoff, en route, and landing. During each of these phases of flight, aircraft incur different channel conditions and different interference conditions. So our techniques are designed to adapt to those conditions. Some accomplishments so far are listed in the upper right. Our dual band radios have been tested in terrestrial settings and have been shown to be higher reliability and yield higher throughput than existing schemes. Flight tests of these radios are imminent. We've had interest from industry and from an ICAO standards group on these technologies. We've also made contributions to millimeter wave channel models, and these will be used by airport network coverage planners in the future for airport networks. We've done successful drone detection tests as well, which form a foundation for new airport detection systems. Some of our key results are listed here. Our project was divided into 6 tasks. Task 1 was a concept of operations that outlined our key future technologies and how to use them. Task 2 was a comprehensive review of existing and planned communication, navigation, and surveillance systems so that we could identify gaps and design techniques to fill those gaps. Task 3 is our dual band air-to-ground radio designs. Task 4 are millimeter wave channel measurements and models and network designs. Task 5, the drone detection, classification, and localization techniques. And Task 6, air traffic management simulation framework for employing the Task 3 to 5 technologies. The photo on the lower left shows the South Carolina Civil Air Patrol aircraft that we'll be using in our flight test this month. The photo below that shows a few members of our team during the installation of their aircraft radios. The photograph on the upper right shows an airport maintenance hangar where we've done some millimeter wave channel environments, a very interesting environment. And the 2 graphs in the middle illustrate our new techniques, improvements in performance, bit-error ratio versus signal strength on the left, and spectral efficiency on the right. Our next steps include flight testing these dual-band adaptive modulation, dual antenna radios, more millimeter wave channel model measurements and models at airports, and submission of these results to channel modeling committees, and additional drone detection work at NC State's AirPaw testbed. Now I'd like to turn the presentation over to the students. First, Priyanka.
In task 5, we focus on detection, localization, and classification of UAVs. The motivation for working on this topic is to reinforce the UAV surveillance methods. In the recent past, we have had many reports of UAVs crashing into sensitive, secure facilities such as nuclear plants and airports. In order for such things to prevent from happening, we would want to have more effective UAV surveillance methods, and detection, localization, and classifications are very fundamental components of that. In particular, we focus on RF-based detection, localization, and classification methods due to some of the inherent advantages of RF communication. For example, RF communication is reliable and works really well over longer ranges, even beyond visual line of sight, and also in line of sight environments as opposed to vision based techniques. And we can also intercept signals passively without having any knowledge of the signal waveform, which comes in really handy when our target is a unauthorized unknown UAV. In the classification problem, as shown in the image on the top, the objective is to identify the source of the UAV communication, and this is done by listening to the signal exchange between the UAV and the ground controller. We then collect real-time data and then use various machine learning techniques to identify the kind of UAV controller that's been transmitting this data. In the localization problem, whose result is shown in the left, the objective is to characterize the impact of antenna orientation on the localization performance. And as we can see in the left, where we are plotting the localization error distribution, that using multi-antenna techniques, which we refer to here as MISO, only offers good performance gain over the single antenna techniques when the antennas are vertically oriented. But in the rest of the cases, the gain is very low. So we are better off sticking to a SISO, that is single antenna acquisition techniques, since this is less complex and less costly and easier to implement. On the right-hand side, we have some results of the classification problem, and we see that using KNN technique, we can achieve very high very high accuracy of identifying the type of UAV controller. In the future, we would like to consider powerful machine learning algorithms that help us fuse data from different sensors of different modalities. So far, we have only considered RF techniques, but going forward, we would like to fuse data collected from different kinds of sensors, that is RF, vision, acoustics, and all other kinds. Thank you.
Mafuza, I think you may be muted.
So I will present millimeter wave material loss measurement. So why do you need this? Basically, material characteristics at these higher frequencies are not characterized nicely, especially for the environment like in airport. So it must be quantified to ensure link reliability. So how do you do this? So for do that, we measure and investigated reflection characteristics of some common building material at these higher frequencies. In this case, we use 60 gigahertz, 73, and 81 gigahertz signal. And to do that, we also consider the distance to material. Distance to materials are chosen 1.5 meters, so the transmitter and the receiver, both antennas, are located in the far field region. We also select several incident angles, as for example 20, 30, 40, 50, and 60 degrees. And based on the measurement data, permittivity and reflection coefficient at these higher frequencies are estimated. The right figure shows the transmit antenna pointing on the material. So now I'll discuss the results that we got from our measurement. So this figure shows the reflection coefficient magnitude with the angle of two material, drywall and plywood at these frequencies. This result shows that permittivity and reflection coefficient increase with the frequency, and drywall are more reflective than the plywood. And these results are very useful for building millimeter wave channel models because this will enable the prediction of channel effects and also the link reliability. And it will also help us to model channel model at these higher frequencies in such environment. And for the future work, we would like to consider some more material in these higher frequencies. Also, we will consider the some frequencies like in 91 gigahertz or maybe tera gigahertz. So we would consider that for material loss, reflection loss characteristics. Thank you. Thank you, everyone.
Millimeter wave communication systems can offer user larger data rates than any previous wireless systems. Although some measurements have been done at higher millimeter wave frequency, not much has appeared in 90 GHz band. The line of sight to non-line of sight channel transition characterization is vital, where channel characteristics can change abruptly, making airport link reliability challenging. This system typically employs directional antennas to ensure adequate link range, and in non-line of sight region must often search in the angular domain for a signal of significant strength. Indoor and outdoor channel transition characteristics should be quantified by change of receive power, signal angle of arrival, multipath reflection, channel stationary distance. This figure shows line of sight and non-line of sight measurement photo at University of South Carolina. Next slide, please. This figure shows a special PDP correlation coefficient for line of sight to non-line of sight transition. A small stationary distance means that the channel is changing rapidly over space, whereas a large stationary distance means that the channel varies much more slowly in space. Here we have some recent result. Received power drop factor of 20 to 50, signal angle of arrival changes by 30 to 60 degrees, channel stationarity distance for line of sight is 2 meter and non-line of sight is 2 centimeter only, which implies that the communication system must adapt very rapidly. Our next step is to determine the path loss and channel transition characteristics for small airport terminal building, maintenance hangar, and airport surface area using both measured data and ray tracing propagation modeling simulation. Thank you.
Okay, Steve.
Great, thanks to all of you. So please, a reminder to enter your questions into the IO tool that is on the screen, and we'll go ahead and ask these wonderful students some of these questions. There's a few in there right now, but please add some more. The first one, Dr. Motolak, you mentioned testing with South Carolina Civil Air Patrol next month. Would this be conducted during the JBC Air Expo on April 9th and 10th?
No, it's going to be a specific flight that we've arranged with the Air Patrol and, of course, are coordinating with the FAA as well. But it's an independent flight.
Okay, great. And some of the work that you mentioned today, and some of the work I've read through as well, is you mentioned that a lot of these developments can really enable a larger number of aircraft to operate safely in the NAS. Now, when you state statements like that, or others mention statements like that, are you referring to traditional aircraft as we know it today? Or is this something that you're hoping benefits, again, 15, 20 years out with the development of a lot of smaller UAS and other vehicles in the airspace?
Oh, we're also considering UAVs, definitely. Some of the detection work that NC State has done with drones and some of our own air-to-ground channel measurements with drones do fit this very well.
That's great, and obviously what is needed because of where we're going and all the things we hear today. But if you think about it, what do you think, everything you've looked at and a lot of the points you've raised to us, and let me ask one of the students this, and anyone can jump in. What do you think are the biggest barriers to the research that you're trying to overcome?
Students?
One of them, in my opinion, would be access to real-time data involving UAVs. And I know that across all the universities and even industries, there are more efforts now in implementing test beds and collecting real-time data, because given that signal processing is really taking the new phase of signal processing is really machine learning now, we would want to take advantage of that, and that would be a great leg up, in my opinion, if we have good data.
Excellent. Zinat, Mahfouza, any additions to that? Some challenges or barriers you think are really, really tough and you're going to dive into?
I just want to agree with Priyanka the same thing, that if you want to collect data in airport, we need many authorization or something like this. So it will take time.
So let me start with Mahfouza, and if you have an answer, if not, anyone else. But how we hear a lot in obviously the media and some of the research going on about 5G and the impact it will have. So there's a question in the chat here, how will 5G affect or impact or influence any of your new communication technologies that you're exploring? Mahfouza, I believe you're on mute.
Yeah, from my opinion, I think 5G will impact use, especially for the airport environment. So we can use those in the like scanner and the both in the ground and also the aircraft system, because we can also use them in the piloted system, because if you use this millimeter wave bands, because there is a like no, wide spectrum, so it will helps a lot to operate in the airport system, and yeah, both in ground and the airplane system. So it will affect a use, but there are actually lots of challenges to do this. One of these, since we know that there is lots of propagation loss in millimeter wave frequency signal, so we need to overcome that. Yeah, so we also can use some antennas, some structural antennas, some like beamforming techniques to overcome this challenge.
Wonderful. Thank you. Dr. Matolak, can you explain a little more about the ATM situation or simulation framework you referred to in task 6?
Sure. That was something that we just, I think, made an initial cut at. There are lots of people working on ATM frameworks for advanced air mobility and urban air mobility. What we try to do is lay out how our technologies, the air-to-ground radios, the drone detection, and the millimeter wave links at airports can contribute to making aviation safer. Well, as Mafuza pointed out, millimeter wave links have wide bands. That means really fast data transmission. So aircraft can react really rapidly when they get the information quickly.
Great, thank you. We have time for one more, so I'll throw this at a couple of the students here. What's it been like working across multiple universities and departments, not just someone within your own? What's it been like working with other universities? Priyanka, I'll begin with you.
Thanks for asking. This is a really good question. So this has been a really good experience for me, this particular NASA project and this particular collaboration of NC State, Boise State, and USC, University of South Carolina. It's just, this is very unique for me because this is my PhD program in my first step in this world, but then I have gotten a very unique opportunity to work on a project that is truly a symbiosis of theoretical and practical work, and it really lets me learn both sides. And I could not have been luckier.
Oh, that's wonderful and wonderful to hear. Thank you. Zenit, anything to add to that?
I also think that I am lucky because in this project I worked with the other two universities. I shared my idea with them. I learned a lot from them, and also in my level, so I can communicate with master student, bachelor students, and postdoc. So I can get sharing my knowledge, and I can get idea from them, and I can communicate with master students. So it's a great experience for me.
Wonderful. Mafuza, same
Yeah,
question.
so thank you for asking. So in my experience, I did a collaboration work with the 3 universities, like University of South Carolina, Northeast State University, and Boise State University. It is actually nice experience to work together in different places, because we did one project. It is like we did attenuation, material attenuation structure in 3 different frequencies with 3 different setup, because our frequency are different, so the setup is different. But we actually did a very nice work because our results shows very good, and we got published those results. So it is really very nice experience, because we can share our knowledge, and we can get also like information from other university student. And also I am actually very glad that I work in this NASA grant throughout my PhD journey. So I'm very actually
Oh,
pleased for that. Thank you.
that is great. Thank you to all of you. We've run out of time. This has been wonderful. So I want to thank Priyanka, Mufuza, Zenit, and Dr. Matolak from the University of South Carolina. Really appreciate your talk today. Really appreciate your answering the questions. Thank you so much. Now I want to take our next step, and I want to introduce our next University Leadership Initiative effort that we'd like to showcase today. We are now going to watch a video about the research the University of Delaware is conducting on the composite manufacturing technologies for aerospace performance. During this video, feel free to enter the questions into the IO tool, and then we'll have a nice conversation afterwards. So without further ado, let's watch the video.